tuple relational calculus and tuple relational domain. These languages, relational and calculus languages, was the primary stone for building the SQL language, which was partially developed at IBM. Then Datalog emerged as a logic language which implemented the logic data model. And last navigational languages includes XPath and BigQuery. Well, the de facto standard language in current systems is the relational model together with the SQL language. Well, I pronounce SQL instead of SQL because it was the first name for this language. And now we have witnessed current towards declarative programming and declarative databases. In particular, last year we held this conference, Datalog 2.0. This is like web. Web 2.0, Datalog 2.0 is the new frontier that Datalog has closed. And this is because there are several needs up today, as ontologies, semantic web, social networks, and policy languages, even optimization. Which kind of systems we can find in this area? Well, the first three you have there are the most classical ones, but here in the University of California, in Los Angeles, Corral, Nail, Wisconsin, Stanford, Arthur, very known universities, but there are also ongoing developments, current developments, not only from academic sources, but also from commercial sources. In fact, this one really has been developed in Calabria and is a spin-off company. From this present deductive systems, we will focus on this. It includes very reasonable support of several features which are not usual in other systems. Well, why it was developed? Simply because we needed a system for students to learn deductive databases. We need several features. For instance, it must be user-friendly. Students must not be have not to fight against the software or the machine to keep things running. It must be interactive, of course, allowing several features. For instance, things that come from SQL implementations as duplicates. This is not usual in deductive databases, but they can also benefit of debugging, not only but they are programming but also of SQL or SQL views. Another thing is that it is related with debugging or debugging as you already know, because of profile as Datalog and SQL trackers, which is a means to traverse a graph of the program, but not following the computational tricks, but from a more creative one. We will see a couple of examples at the end of the talk. Well, with other features in implement this, for instance, support for new values that is unknown information. and relate to this value some operators like outer joins that come from relational databases. Aggregates also need a feature in SQL work, and they implement other operators as except, which need some form of negation. In this case, this will be a stratified negation that we will see later. And integrity constraints are first specified in the relational model as primary keys, foreign keys, for instance, and are implemented in most current relational systems. Well, let's also implement this and for support for SQL constraints and Datalog constraints. Integrity constraints must not mix up with constraints with constraints coming from other fields as constraint logic programming. I am talking about strong constraints, which are constraints that a model must obey. Also, arithmetics, a type system we must use a type system in SQL and can use a type system in Datalog. Also, the system implements some program transformations both separately, we call it the mean and performance for simplifying data flows. Then, recalling Manuel Carro talk, it implements tagging. SQL as of this includes several parts of the language. The data with language, data manipulation language, and the data definition language. Usually, these two first parts are known as data manipulation language, but I include them because it's more helpful from my point of view to separate query from altering a database. Well, how Datalog and this SQL live together? I think this. Well, because there is a deductive engine that will process both languages, because SQL views and queries are translated into Datalog programs. Then this engine will execute and compute the meaning of the queries. So we are able to query SQL view or table from Datalog, and also we will be able to query Datalog relation from SQL. In addition, we can open our system to an external world here with these connections. So we can access tables, views coming from other relational systems, Sofware, Microsoft Access, Oracle, and even by text, separated values, as you can find in Excel or other systems. Well, how is it possible from our engine we will inject statements and we will retrieve the results, and they will be cached. They will be cached by the deductive engine. So this data will be shared by SQL and Datalog. But let's have him use this for reset also. For instance, we have developed this case generation for SQL views, also for debugging the Datalog programs, and FTO also. This is not the last version of the slides. I have them in my office. it was the change from one computer to another. And also another proposal for outages in Datalog. It had been used in thesis, papers, academia, it's a system which has been widely used. Its impact factor can be explained, or can be viewed because there are a lot of downloads since its inception. All the downloads, for instance, are created by well-known systems XSD, DMU Pure, get another Pure, and so on. Well, in Wikimedia it was the very first system, but I promise you that it was not me responsible. For installing this, we can follow a very straightforward procedure. Simply copy a file, a binary, and then execute it. Or we can use sources and load them and console from a product interpreter. Also, we have a Java application which is intended as a configurable integrated development environment, and have several windows, buttons, projects, and so on. It is really portable. The slide was about the Windows, but this is Linux. This is also Windows Windows application. This is Mac Snow Leopard, thanks to Gabriel, the port. On a terminal, there are several links. Well, with respect about the implementation and the tools which have been provided and distinguish this system from others can be found in several publications listed here. And this is, for instance, development and finite domain constraints. For instance, for the state generations and for the type system. Well, there was also this talk which showed why deductive databases are useful, why we start from the relational model. Well, languages stands for relational algebra and goes to SQL and Datalog, whereas SQL enjoys many functionalities. Datalog allows neater formulations, as we will see. And how to start this? With some data models, and we base our grounds on this. Well, this is the very first point of talk about data models. And if you recall, the relational model was developed several years ago, about 1970. It was developed by initially was called an opposition to this model. Well, it's true that current database management systems do support this relational model, but it's an extension of the extensions of these models. In fact, that they depart from the relational model and introduce several cloud extensions as duplicates and null values. Could provide the original algorithm and also the calculus. Finally, SQL has been stated as standard by Python. Well, some concept about this model we must talk about schema, instance, and constraints. I think that you recall this from higher education. These are the initial languages what we developed. Relational algebra deals with several basic operators such as selection, which is row filtering, projection, column filtering, renaming of relations and also column, the cross product of relations, the union of relations, difference of relations, and it is made from a logic model to implement this or to express this. SQL in fact can implement this relation for select operation. This is a clause select some columns from some relations. It has a projection list that after the select clause, and the renaming has been used with articles and with cross product is included as relations separated by commas after this cross from the union is set union and the expected difference set difference, except or minus, which is the other keyword used for set difference. Well, original languages can do that. Row filtering, double filtering, union relations, even evaluate expressions in terms of constants and values in that relations. But we need some sort of generalized projection which is not found in the original proposal. But all current systems do not implement relational model, but an extended relational model, including this type of projection. Well, this was what relations cannot do. What can they? What cannot do relational languages? For instance, if we are building a car and it is composed of pieces which are related between them in a kind of tree, we cannot know with a single pulley what is the total cost of the car, counting all the pieces that are below some quantities in particular. For instance, a wheel is composed of several other parts, radius, nuts, bolts, and so on. So we simply need recursive. Relational algebra does not do recursive. In this example, we have instead of a car, a bike. Bike has two wheels, one frame, has several spokes, radius, tires, etc. And if you want to find all the components of the bike, you start from the value of this tree by a recursive exploration. Traversing, you can know which are all those components. But relational algebra is not able to do this, because if I want to know which components are of the bike, I know that the bike is composed of two wheels, a bike is composed of one frame, a frame has one seat, and so on. Then I need to join tuples of this relation with other tuples from the very same relation. How many times? Well, it depends on the depth of this relation. And this is not a good approach. So, the logic is here to provide such kind of recursion. Relational database is distinguished, as I already said, these two parts of the language, but deductive databases do not. They are mostly about formulas. Similar to the relational databases, Deductive distinguish between an extensional database, which is the base relation tables, and the intentional database, which we can say as the views in a relational database. We call first order logic a literal language. Is given by a signature in which we can express constraint symbols, functional symbols, function, predicate, and variables. This logic will be enough or will be adapted to provide meaning to deductive databases by interpretations. Because an interpretation tries to capture the semantics of that language as following a method of interpretation. We know that rules in a logic program define possible words of models. So a model will be a set of rules that make an interpretation it's an interpretation that makes to all the rules in program. But there are many models for a program or set of rules. But luckily, with application, we can find a single model. It is needed for implementing or representing many of the operators in the relational algebra. That's all. But here we can see an example in which we see the substitutions for rules 1 are 2, so that this is a model which makes R1, Q1, Q1, Q2, R2, and for otherwise. With some such substitution, you see that all the possible interpretations of rules are true. Okay? There are cases such as this when substitution by true, we have false unprecedented, but in the interpretation, is really true. But for the second sequence, this model is a model of the program. But it's not a minimal model. However, it is. And it's we assume R1, Q1, R1, R2, and false otherwise. And it is consistent with this fact. This fact will belong to the extensional database. So, what a typical user would expect from a query language. This is not a product point of view, but it's a database point of view. Expect finite data, finite computations. In order to do that, you must cut down some features of the language. This means that Datalog will not be a composed language, specific composed language. Then, of course, all this logic will be cut in some aspect by only allowing all clauses, such that long instances are such clauses, we can check for unsatisfactority of valid subsets of current tension. To ensure finding computations, we are invested to non-recursive type of functions, and then we can find a finite temporal expansion because the program generates finite in this case. Then every predictive is written by clauses already known with atomic formulas and it has at most one positive leader. Then this can be rewritten by a multiplication. Well, now that Datalog is based on kind of programs composed of clauses, its syntax is similar to Prolog, and it was introduced on 78 by 11 Linker, and also used as a condition for expert systems, which are not usual today. We not speak about such expert system, but knowledge-based systems. And this language is based on Prolog, and whereas in Prolog we'll talk about predicates, in Datalog we talk about relations, as well as in relational algebra. We do not speak about fields but codes, and in relational algebra we'll speak about expressions, but we are talking conceptually about similar things. Predicate is similar, corresponds to relations in Datalog and relational algebra. In what differs Datalog from Prolog? Well, Datalog, to make different involves finite, does not allow function symbols in arguments. For at least they are restricted in some form. For instance, the depth of that symbol, some systems do that with 2 bits. There is a limited depth. Facts in Datalog are round. We call this limited safety is crucial for finite computations. And for reasons, always there are just mentioned more favorite point of view, tuples, the meaning, and from rules and facts. But one key aspect of Datalog is that it is truly declarative. Prolog is not. Because the closed ordering is irrelevant. I can mix all clauses with no semantic changes. I can query the same program by switching clauses or even goals and bodies. The answer is the same. Also, there are no extra logical constructors as we can. Well, this is the syntax of Datalog. From a set of numbers that can be a rule with head and body, or only an head. In this case, the head might be ground, which is fine. The body can imply conjunctions, intelligence, and also the implications, as we will see later, but not in this stage. Integrals can be add-ons, built-ins, which are also sources of problems, so we will see. And a query can be literal, or even conjecture queries, which are composed but more than one literal, either conjunctive or semantic. This is an example of a Datalog program, and here we have the classification genealogy and several persons. Is defined by several facts, father and mother, and several rules. This problem can be queried by find of x and y, or variables are uppercase, and a model for variable M becomes the father of M, or raising the mother of M, and so on.
And we get all fathers and mother as a union of these two relations, father and mother. Recursion is also allowed. For instance, we can find ancestors of persons in this universe by this recursive call. This is set. This language is truly declarative because you can switch the base case of the recursion, the query still succeeds. There's no need of order in clauses. Well, I think that all of you recall what fixed point is, and for computing the meaning of recursive predicates, we apply the least fixed point of a function. In this case, the function is the natal program, which is applied to a set of tuples, returns a set of tuples, and we get the same tuples as input. We are down. Fortunately, we only have a least fixed point. But, as already said, there's a problem with variables in facts and also in heads of rules. For instance, you can see that this rule if x, if r of y. What does this mean? What is the meaning of this? What is related that variable to anything? So anything. Several possible, which is the meaning. I cannot say it's true for this element of the universe. Which element? The same related problem comes from built-ins x less than y. How many pairs we can find that needs such a relation infinitely many? So we must restrict such variables. This is the notion of safety in deductive databases. A rule is safe to be safe if all its variables are limited, which is also known as range exception. We must be sure to know a finite domain for each variable in a rule. Otherwise, we can get infinite answers, and we do not want such infiniteness. We can define a limited variable in a rule as follows. We say simply to be sure that there is a data provider for each single variable in a rule. For instance, variable x at the constant have to equal a, so a equal x is limited. We have must be limited already. So bottom line, we can say that any variables and variables in distance must become ground. No one can be unlimited. Otherwise, can provide a final answer. Well, the question is opinions, okay, but really, Datalog is as powerful as reasonable algebra. Let's see. Selection is quite easy to represent in Datalog. We have relation X has two arguments, name and supply number. It can be seen as key. And if we're interested in supply name, what is the supply name for this ID? One complete, then complete, is the select name from X for super number is 1. And in that about simply write down this query X of 1 and Y. This is the argument position for the identification. This supply number. And we get the name in Y. Projection is similar, but now we can use this anonymous variable which is started with this underscore. Then we will get values for arguments in the second position. This is distinct syntax for SQL or SQL and Biblioteca. Here we have a notational by name, notation by names, and by position. Relational algebra also allows not only these argument names to be specified, but also positional notation. This is for the first argument, the second argument, and so on. Also, the naming in SQL can be done with clause. We will name this relation, which is a subject from relation. Also, if we want this argument. In Datalog, only with one line we are doing the same. For example, this relation with respect to the second argument, y. This neat formulation. The cross product or Cartesian product is similar. We only have to specify from list those relations separated by a comma. It's similar in Datalog, but here in Datalog we must specify also the arguments explicitly. Set union can be also done in Datalog with the symbol positively. We can write down two rules. The first one with this code and the second one with this other code. But what about set difference? This is a problem in Datalog because need indication, great indication. This is a source of problems. This query, conjunctive query, would compute the difference among these two relations. For example, pair of arguments x and y. So, for the Datalog to compete with respect to relational algebra, we need a form of negation that we call, but our clauses do not allow this. Okay. Well, for SQL, we can find different proposals in terms of we can find or not negation and even functions. As I said, some systems do allow this, but it is for limited bounded depths. Well, I can have simple data. We can have developed function, developed negation, or developed function and negations with ellipses. Thinking about what kind of programs can be taught by and using Datalog version. It can be shown that languages using derivatives in calculus and not yet about negation are equivalent, semantically equivalent. At the end, only a question of syntax can write the same queries in different languages, but the meaning is the same. So we need the negation device. But what negation stands for? The complement of a relation, but it's not a well-defined term. And this complement should be computed with respect to a domain. And what does this do by relation operator? The difference operator. And both in relations are one because they come from relations which have been already known, even if they are from the intentional database. But one, because if we didn't know the actual domain, complement will be infinite. Just in this case, when we are talking about open arithmetic, such as integers. But even integer, what is the complement of the negation of a relation? Before that, it's not really C parallel or 6 parallel allows for unbounded arithmetics. Also, it is not the only problem, but consider that variables are not limited in this case. Vectors which are made, which are not married. It's a thing this rule. Someone is matter who can join made with complement not married, but what does that mean? This X is not married with everybody in the universe. So, variables in that negations not be limited. If we submit this query or try to assert this rule in this, we get an error. This expression, this code might not be correctly computed because this variable y is not range restricted. So, one point we have to be sure is to limit variables. But this is not the last one. Maybe for you we call Russell paradox. Rafael Caballero has told you about that. You can have multiple solutions, multiple models, minimal models, minimal fixed point. Then we need a way to choose the minimum for this. How can we do it? One proposal is certified negation, which is a property that there are programs enjoy. For this, we construct a predicate dependency graph, which consists of predicates which are connected to other predicates appears in rules. And it said that it depends on F if some rule with predicate T in the head content S, or simply some predicate that depends on S is invalid. Okay? And this is a case of differential, and we must be sure for a program to be certified is that if a given predicate depends on the negation of another one, then this one cannot compare first of all. That means we cannot find seconds in a graph. It involves guessing. Well, if a program is certified that way, then predicates in the program can be partitioned into strata. The first one, stratum 0, and if all extensional interface predicates, such as those stored in tables. And for the fifth stratum, the predicates one types of tables in the stratum I and the lower stratum. It depends on the negation of S, then S must be in a lower stratum than when we are isolating that predicates, for instance, if not Q, then Q should be in a stratum which is lower. Because intuitively, this is P. Intuitively, we must compute from lower stratum to upper stratum. Give a meaning to the program. So, but one negation still requires shuffling. And such negative codes are not allowed to be range architecture, but they need its variables be limited. Then provide static semantics supposed to write programs following this intuition that I have provided you already. But this is not the only thing to consider. Not only semantics we are able to, but we must always speak about performance. We need a practical system. So this implements styling that you already know, as I said from the manual talk. And it is don't try it, it's at this name. That it is read by the query. The user poses subnets a query, and then it is computed by the startup until all meaning is computed. This means that not all the semantics in the program is computed, but only the needed predicates that are involved in a predicate dependency subgraph, starting from the query. If we load our program, we can build a dependency graph of the whole program. But a user is not interested in the meaning of all the whole program, but in a given query. Well, this restricts the computation to that query and only involve predicate. Our aim is a declarative that provides both termination properties and performance, making some points of any program to be linear. Exponential programming. Well, this is the example that you already see near the top of manual partial products. how you can consult in this. This is a command for consulting this program. And this one here, this is not a program that can be stratified. No? If we try to execute this query, find the people which saves to other people. Then this is able to return whether it is able to say divided, but I'm not sure about whether it saves itself. So it is undefined. Does this mean that this implements three value logic? No, not completely, because it is intended only for rather small or twin programs. Implementation is not complete. It could be, but it is not. As I said to you before about computing a subset of the meaning of the program, identify a identifiable subprogram for a given query. For instance, if we console this program, then we can submit this query. Who are the ones in this database? Oh, no problem. This is a query. Let's find a subprogram. In this case, straightforward because it's a ventilation, and it can be accepted computer. There are no undefinedness. Well, our elimination? No, there are. Elimination, as already known in the programming arena, is a source of problems and fixes. There are proposals in the deductive fields such as stable model semantics from Helpon and Lipsit, we found in semantics, and for the logic, which is very recently implemented in a system called for QA. And introduces not only true and false, but also inconsistent. It's called undefined here, and also unknown, which is related to data which is absent in a database. In SQL, you can find this kind of data in the null values. Well, but what we need are practical database systems, not free systems. And we need efficient systems which are able to apply probably need that is abuse also features as indexing or scalability, but here in systems which are maybe dealing with millions of tuples. With respect to explosive power, we need calcium, we need several constructors to implement basic operators or coming from the relational model curve. There are some other features that must be practical systems, such as, for instance, evolution of expressions, something which is really basic, the ability to compute, to evaluate the expressions. Interestingly, the central system can do all arbitrary expressions, such as DLD. I don't know why, but it is so. In this, you can evaluate the expression in the most prolonged way. X is the square root of 2, and also using equality. Equality will try to reduce expressions and try to find out whether they are equal. This is also available for other comparison operators, greater than, less than, and so on. But, as expected, they are source of uncertainty. Let's consider this program. Here, we have the relation P of only one argument, integer. The base case is P of 0, and the recursive case is this, which computes new numbers, incremental numbers from some base cases already known. What about if we submit this query P of X? Well, we will obtain an infinite set of pairs in the answer. But look at this. This rule is safe from the point of view of variables of minus equal. But what is this built-in X? Is a generator of infinite tuples. Really? If we think of this is a quality. We relate to objects to be designed. So, infinitely many objects could be designed. And this is what is happening when we are talking about unbounded arithmetics. Well, another feature that we must find in database are strong integrated constraints. It comes from relational database system. So, for instance, a constraint initially known as domain constraints, that are the possible values a variable can take. Primary keys can be distinguished a single tuple in a relation. So, in case, if given argument must find a counterpart in another primary key, another relation, consistency constraints, we are ensuring that a given argument must known values and not null values as in SQL, and check constraints, for instance. But there are other constraints as case functional dependencies and usually defined integrity constraints. And all of them can be expressed in that as assertions in Datalog or in SQL statements. Some things won't be done in SQL and either in Datalog. Well, with respect to types, we have focused in types as of SQL because we have languages accessing the same database, and then these user types as defined in the standard are available. How can we declare types for a predicate with this assertion? For instance, type P, which has two arguments. The first one has type integer and the second one string. Types are not only the extension of the database as in relational databases. In relational databases, we create a table, name of the argument, type of the argument. But what about views, intentional expressions? We are not able to express types, but Datalog we are. How? In the same way as before, but considering relations, which can be recursive, of course. In this example, we have a program which is allowed in Datalog, because we had the definition else argument, which could be given a string type, and T, which is defined then of an integer constant and a call to another relation S. Then, if we have this program and try to assign types, we're not able to do it because type checking will raise an error. There is no type tuple covering the meaning of T, because in the meaning of T we find A. Well, we are able not only to define relations as in the relational model, but also propositional relations which has no argument at all. For instance, we are able to type a given relation A without arguments. This is legal. And the table is defined only by this. This is also interesting for several special tables, like the dual table. This dual table is known because of Oracle that introduced it. If you need to evaluate an expression, but you do not need really a data source. What is the square root of 2? Well, select the square root of 2 from dual. Which is dual? So to define relation. Okay. It's not a data provider, only one row and only one column, but they are hidden to the user. Types and domains are invariant. Next way, we track tables this way. While in Datalog, we can do the same. But notice that I can provide argument names. For instance, they are, as already said, equivalent statements. This is an assertion that claiming the relation S in the same way as the S-SQL statement. They see that it's different, but we are doing exactly the same. Well, there are also other constraints, like the existence of constraint, that in this case we are imposing that the second argument of S is not known. That is, we are requiring complete values for each tuple of S in the argument name. A primary key constraint can specified as usually SQL Datalog simply saying that primary key of S is that argument, the supply number. And here you can see that type checking or primary key checking is working. You can turn it on or off with commands, but in this case, checking is on, it's enabled. So if we try to assert a new tuple with the same identifier, it is rejected. The second one is rejected because it's a primary key violation. Candidate key constraints are not provided or not supported in SQL standard, but can mimic this behavior with indexes, with non-duplicates. This does not provide these indexes up to now, but it provide this clause similar to FileMaker. And also with this assertion. What we have read here was similar, and I will not go into more details. Only to mention that functional dependency constraints are not present in SQL, but they have added this as a dependency between arguments. You know that FileMaker is a particular case of a functional dependency. You should find integrity constraints in class in SQL. That is triggers and set constraints, but a limited sort of things can be done inside this clause. Rather, in Datalog you can do whatever you want, because you express integrity constraints with Datalog programs. In this case, it's only a simple assertion which consists of a conjunction of a relation to and a condition that must be complied by all instances. In particular, we have seen here that all tuples of T must be at x less than 0 or x greater than 10 will be discarded. That is, it's the contrary as in SQL. In SQL, we say, well, this x must be between 10 values. I want to be x between 0 and 10. But in this way, consider that body of the clause is stated otherwise. So if you try to assert tuple like this, it will be rejected. And you will inform me why it is rejected. So you should find integrity constraints can be used for a number of things. For instance, in graphs, you can use it to detect cycles, or simply to know or to disallow a path from a single node to itself. Here you have a program that defines this graph and the span among these nodes. So this integrity constraint is asserting, is stating there must not be a path between x and itself. But this is rejected because there are opening values in the database. What are them? Okay. The system is computing this integrity constraint, and it is checking that any tuple in this meaning is not in the minimum parameter. Well, another feature which is useful in current database system is duplicates, but they are also a source of flaws. Code already said if something is true, saying it twice does not make it anymore true. We do need to duplicate things. It is a reality that current applications are using the application, for instance, counting persons, counting elements in foreign relations. So I want to support SQL to work with new duplicates. A notion for multi-set of batch and also duplicate elimination is correct. Some issues that come from using duplicates, and they see here. You have two statements that should be semantically equivalent, but they return a different number of tuples. We have check about sets, and here we have joins. Here we have more tuples than here. This is not only the first issue, that is, a programmer should be aware that the same semantic might be delivering a different number of tuples. For counting tuples, this is important. But it is not the only problem. It's a problem for implementers, for system implementers, because they declare some optimizations and make this optimization even more difficult. Because anytime you are optimizing some video, then you must think about what tuples can be covered. It depends on relations that depends with another stages. In this, duplicates are disabled by default, but you can turn them on, enable duplicates via this command. So if you assert the same tuple 2 times, then you have as answer a multi-set or a pair. Also, rules can also be source of duplicates. For instance, this rule is of x if t of x, then it actually you get the same 2 tuples. Okay? Not only this, but also recursive rules are source of duplicates. We assert this apparently non-terminating rule, which we know that in Datalog will ensure termination for all programs, including this kind of rules. Then we get 4 tuples. 2 from the definitions before, that's like plus 2 coming from this rule. 10 from here. Well, SQL implementation support this, but also SQL implementation support some feature about recursion that we will see. Well, if we allow duplication, we can also a way to discard them in programs. Well, this can be done with this thing. Make this thing. And if the same program before, use this. Well, use this thing effect. This is transformed in Autor. Still with some meta predicate. It cannot be given, but we do need a relation which represents that being. This is done in general and automatically by the system. Here a new rule has been built answer of x if we can prove this thing of the missing thing for that argument. This is asserted to the database, it is computed and then removed. But in the meantime, the answer is some. In SQL, are limiting the behavior will select this thing start on. Well, subjective tools. If you are accustomed to product, you know that there are set variables in Interactive like find all, set all, tag all. They are not bound after the completion of the attribute code including such method predicate. Well, this is something in Datalog. And here, for instance, we can submit this query for another relation. Now we are assuming it has two arguments, but we are requesting distinct tuples with respect to x. Tuples which have distinct values in the first argument. Well, this is okay, but if we are according to another relation or accept variables, this is unsafe. In fact, we want to check because this is a variable that must not be bound for any other case in the code. So, the system warns you that this is unsafe, and even if separately program transformation is enabled, then this query is automatically transformed by switching simply the order of rows, so that now X is a data provider. Where is that come from? Well, it comes from how things are computed. In fact, following SOD, the colors left to right order. Practically speaking, this might not be a problem, it could be there in another way, but up to now, this is identified as a problem and projected if it is not, it cannot be fixed, or if it can, then by switching to those. How many minutes? 6 or 15 minutes, 20 minutes. Yeah. Well, another important feature of database system is aggregates. And we need to compute results of a function of its range over sets, not over single complete values. For instance, compute arrays or some numbers. So we can find several aggregate functions which are similar to SQL functions, but you can express in the heading part of the statement or even in the projection. Well, in these functions can be written in a meta predicate called group by, which is grouping tuples with respect several columns, and so that there are some conditions over such groups. We can have here a closed heading in a SQL statement, say, well, that and the number of the employees in a given department is number. This is how we, for instance, where the number of employees for each department given this table employee, name, department, and salary. We count in the result R equal count the employees, but grouped by departments. Again, this field is translated into a rule which is an automatic view, because true values are meta-predicated. No strict meaning, but in the context of that rule. Very simple. We have an 11 double and a number of 11. 3 plus 2 plus 1, 5 counts. Aspect. In the next slide, we count the number of effective employees, those that have assigned salaries. And it's clear that there are several new values. These are not included in the answer because we are waiting to the count over salaries. So, rules are discarded from the computation. And then we have 7 counts. Instead of expected as simple. Well, another example, time does not to me. And another example of aggregates this is using predicates. It has seen by meta predicate that involves function, aggregate function. But now we're talking about aggregate predicates such as count the number of elements in a given relation, this relation. So this can be one goal, one which doesn't need any grouping. There are also functions for counting distinct. Well, for example, minimum and maximum. There is no need to discard duplicates because if we are looking for the minimum value, it's only one. Well, however, we can express grouping with such predicates. Before, we used this predicate by employee, by department, and we were searching for the number of employees in each department. We aggregate predicates. We can do a similar read with this. We count the number of employees, use count over the relation employee with respect to the salary, and the result is count. Look at this. This is quite strange. We are submitting a rule as a query. What does this mean? This is a temporary view. It's similar to what happened with that use of meta predicates, which were translated into rules. But now I am expressing exactly what we want in the head of the rule. This is like why this rule, then assert it to database, then compute, and then discard the rule. But what is interesting in this is I am specifying the grouping where C is the result of the count, D is the group by criteria. We are grouping by departments. So we are processing the rule in the context of the program, and we have the outcome of the rule. Well, arrays can exist with Gaussian. Simply here, a program to serve or to compute sorted paths in a graph, that here we can see the difference of the formulation in SQL and Datalog. See that here in Datalog, has formulation that neater, that more compact, more readable, more maintainable. Well, and as for duplicates, aggregates must be restricted to set variables. It's similar to what I said about duplicates. Well, algorithms. Not so much time, but what do we need gets to implement SQL behavior, in particular null values that we have seen in some examples. But what is the semantic of nulls in SQL implementations? Well, it is rather strange, because if we compare two constants, we can say, you can say if the outcome of that comparison is true or false. You can do it, but what about a constant compared with a null value? This is a null value. We do not know. Can be anything in the program. It's information which is not in our database. Well, what does SQL do? Instead of returning, I don't know, they say it's false. But that's wrong, no? So, several people say that SQL implements three-value logic, but it is not. So, in other words, if I pose this comparison, is equal to what? A is equal to A. Of course, it should be true, even if it is assigned a null value, because if we know that value, will be the same. So it is the from way to the false back and recursion. So false is used to represent an unknown. What about this? It tries to do a similar thing because we want to mimic SQL behavior. But now in those our values are distinguishable. Its null value is different from any other null value. This means that if we compare the same null value with itself, I can say yes, they are equal. It's true that they are equal. It's false that they are not equal, and so on. But still, we have the same problem as SQL. They are a slight difference with respect to this SQL, but this is only for implementation needs. Usually, when you find nulls, they are represented in this way. A term which is assigned a unique symbol identifier. Well, still, we are in a two-value logic, more or less. I would say I am in a 2.5 value logic. Why? Because which can be detected as undefined in the answer, as in the Russell paradox. It's not complete. Well, implications are in the same way as in SQL, distinguished. So, discarding duplicates for a set of nodes? The answer is only one. But if we want to take duplicates, we can the tuple have n nodes, get n nodes, maybe duplicates. Okay. So they suffer from some flaws. They are really used in current applications. Several other systems that implements or those that provide support for nulls. RQL, which is used in the semantic way. QL, which is was in development, and also XSD, that was already noted. But it does not provide outer joins. Well, in this we have left, right, and full outer joins among two relations that must commute to a condition. It's the same as in SQL, as the next slide shows. SQL we have, for instance, self-start from the condition A left join B on condition x equal y. However, we have a more neutral formulation, but meaning the same. We can also make composition of these functions. We do not have to struggle about syntax. In SQL, if you have used outer joins, we know already that there are combinations that are not allowed. Well, one does not know, but they are not in practical systems. In this, you have no problems but applying several compositions. Well, outer joins are handled by program transformations. See. Current relational database management systems suffer from several limitations. For instance, recursion. We cannot use duplicated elimination. For instance, union is not allowed. We must use union all. So you cannot use distinct aggregates, but be certified. And also, recursion uses an explicit recursion that has in Microsoft SQL server. Also, process linearity. That means that only one recursive call can be in a body. Also, certification of other operators as stated in SQL standard. And finally, MySQL does not allow recursion at all. Well, this is a simple example, but this example can be executed in this because this does not impose any restriction. In syntax, well, the only restriction are those of, like in particular, statification. Programs must be statified. Well, also we can use a simplified syntax. Statements are more readable. Well, other feature that includes this are the declarative debugger. Pai Caballero already talked about this. We have no so much time to stop here. And not only debuggers, but also we have tracers. And what is the trace? Well, it is very similar to what algorithmic procedure does, a declarative procedure does, as framed by Raphael. But visiting all the nodes in given order. Then you can have a picture of the graph for both Datalog and SQL. Also, we provide a SQL test generator. This is also related with Elvira, one of the first talks. We can, given the program, provide positive cases, negative cases, and both positive and negative test cases. Well, other features of this supports recent features which are needed. For instance, this is not explained, it's a lack of time, but in the information of how the journals operation appears unsafe rules which are treated especially by the time mechanism, because some nodes are treated as data providers, but disability stop that. Only say that tabbing must include a special equipment for such operations. Well, we have a preprocessor which is in terms of the primitive framework, transformations, analysis, and so on. It can use a development mode to inspect exactly what are the representations of nodes and also how programs are transformed. We can also inspect how SQL statements are transformed into Datalog programs and several. Also, we have back processing programming by programming. Things coupled with logging, we can dump results to files. This is interesting, or having of interest to several users that use this system to couple it with external applications. But for this net, we have provided in the last release textual area for communicating to other applications. We have seen the relational model is key in coding systems, but in particular an extension of that model. It's not only complete because we are not talking about set but multi-set. We are talking about information which are positioned, and SQL has 6 types related to human speech. That way, the statements are longer, but benefit from many functionalities that maybe not all the system enjoy. But allows immediate formulation because its syntax is oriented to formulas, and it really has margin recently because of needs coming from these areas, for instance, social networks and optimization. But syntax, as already said, is not all important. A practical system is the key. I'm not saying that this is a practical system. It is a system which is oriented to education, but it has no performance at all if we compare it with, for instance, XP. This other system. Okay. However, it has been widely used, has more downloads from XP or other systems as Datalog, new program and others. But there are many other things to do, make this system really practical, like Informatik and report. Well, with this, will stop about
Yes. Thank you very much. It's nice to having a counter, and then you can, the counter reach 138, and then you are reaching 140 slides. So, anyway, questions, please. No question? Everybody satisfied?
Which language is the interface? Which language is the interface with this?
The implementation language you're asking about? Yeah. Which language have you used for implementation?
Prolog. It is implemented in Prolog, in 6 Prolog, but there are versions for several 6 Plus, Sui Prolog, Linux Prolog, Chao Prolog. You have a common interface, and then some other interfaces for each complete system. But and the binary is built with 6 Prolog. There is a full feature, OTTC connection and so on, and others as Chao Prolog and Sui Prolog are not complete, because they have OTTC connection and finite domain constraints, while not a full support for such finite domain constraints, which are needed, for instance, for type checking and also for test case generation.
But if you want to use this from another language, you want to have query from another language different from Prolog?
Yes. What do you mean? That moving the implementation to another language, or just?
I mean, in the same way I can access a database from Java or C with a...
Oh yeah. Whether you can connect
Connect with other system, with database system.
Yeah.
Yes.
No, I mean...
Can you query the system using other languages?
Exactly.
Yes. In the last version, 2.5, you can use another language, any language, but any language, any language which supports standard streams. Any. Because there is a textual active. And you mix some commands or quiz statements, and then you get answers in a given format.
Any other questions?
You can save a program in a file, in a text file, to have persistence of the database. And what is the limit of the size of the database?
Well,
it is limited by the computer.
It depends on the system, the operating system, because if you have 32 bits or 64 bits, it depends the amount of data you want in memory, because this is a memory system. However, if you use OTTC connection, data is persistent and files, so you have no limits on tables. But if you query a table which its result is written the available memory, but who needs such an answer?
So in principle, there is no limit on the size of the database.
Limits
Using those
are in memory. Because you are catching, you are used a cache to of answers. Then the answer is Q, and then not fit into the cache.
Thank you very much, Fernando. This is the end. I would like also